Okay, I'm going to touch a little bit on 12.1. I'm not going to go through the entire PowerPoint presentation, but I'm going to work an example out for you of the basics, and then I'm going to go over the practice worksheet for you. Here we go. So 12.1, inference for linear regression. It says we need to check the conditions for performing inference about the slope, beta of the population, the true regression line. So all of our testing and confidence intervals are going to be based on what we think the slope might be. So always beta for slope. We're not really going to test anything about the constant y-intercept or anything like that. It's always going to be based on the slope. Okay. Interpret the values of A being our y-intercept, our constant. B for statistics, we use B as our slope, not as our y-intercept like you did in algebra. So A is the y-intercept, B is the slope. S is going to be the standard deviation of the residuals. SE sub B, that's the standard error of your slopes. And then R squared is still your constant of variation. Your R is how good of a linear fit you have, and then R squared is how much variation you have in your Y depending on your X. And we want to do that in context, all of those things. And then determine the values from computer output. So you're going to see that I'm going to pull up an example and work it out for you, but this is what they mean by the computer output. We're going to have something probably from Minitab or something like that, where we have to pull all the information we need from this chart. So the constant is your y-intercept. So we're going to have 38,257 represent our y-intercept, which is our A variable. And then from the chart, we have the number underneath that represents our slope. So for the example I'm going to go over in a second, miles driven is our slope. So negative 0.16292 would represent our slope. So we have a negative slope. And then our S is the standard deviation of the residuals. For this problem, it's going to be the 5,740.13. And then the SEB, the standard error of the slopes, is going to be on your chart. It's going to be next to your slope, and it's going to have the SE coefficient. So our SE sub B is going to be 0.03096, and we will use that when calculating our confidence interval. So we'll have to know where to pull that from. It says we also need to get the R squared, and we have R squared as 66.4%. We're not going to use the R squared adjusted. We're just going to ignore that. So it's just the R squared. So make sure that you do just completely ignore the R squared adjusted. And just kind of a reminder in case you forgot, if we did need the R value, then we would take the square root of the R squared, but then we would also know that it's a negative, because if your slope is negative, then your R value is also negative, since we have a negative line, a negative sloping line, if you will. Okay, so that kind of identifies where you get everything from. It says construct and interpret a confidence interval for the slope beta of the population true regression line. So I'm going to show you how to do that with the data that's given here on our calculator. Our calculator will actually construct a linear interval for you, a linear regression interval for you. It will also run a linear regression test for you. The problem is they don't always give you the data. Sometimes they just give you the computer printout, and so you have to be able to calculate and find the interval if you don't have the data given. So I'm going to show you with this one example both ways of doing that. On your practice worksheet, they're only going to give you the computer printout, so you won't be able to put it in the calculator and actually run it on the calculator. So it's kind of, you know, a problem for us, those of us that really like to use the calculator. They're going to force us to do it by hand by just giving us pieces of information, not every single data point. And then it also says we're going to perform a significance test about the slope beta of the population true regression line. On your practice worksheet, they're not going to actually have you do an entire test. They're going to give you the setup of a null and alternative hypothesis and ask you to compare it to a confidence interval. And basically, if you know the value that's in your hypothesis, if it's within your interval, then you're going to say you fail to reject. And if that value is outside of your interval, then you are going to reject. So we're not going to really truly run a test this time, okay? But before we do the practice worksheet, let me walk you through how you would do this example if you were just given the data and you did not have the computer printout, what you would want to do is go into your calculator, and on miles driven, you want to put all those values in list 1, and the price in dollars, you want to put all those values in list 2. So before I even get started, and I would encourage you to do this as well, and you see I just messed that up, you want a second plus 712 to clear the RAM on your calculator, and then you want to go in and do stat edit, and again put miles driven in list 1. And it is going to take me a few minutes to do that, so bear with me. Hopefully I won't make any mistakes here. Hopefully you're working along with me, so you're typing these in the calculator as well. If you didn't even have a calculator when you started this video, then pause it and go get yourself a calculator so that you can be inputting these values with me, please. Okay, and notice, because it'll come in, it'll be important later, notice that I do have 16 points. So we have 16 pieces of data. So now in L2, I'm going to go in and put the price in dollars, put all those values in. Okay, so luckily all my lists lined up, so I've got all my data in. I just hope that I did, put it in correctly and did not make any typos, because that was kind of a lot to put in. And now I want to scroll that back down if it'll let me. Okay, and I want to show you how the calculator will pretty much give you all of the information that they're showing us how to get by hand. So once we've got our data in our list, used to what we would do is we would go stat over to calc, and we would run number 4. We would run the linear regression, and we would get our slope, we would get our y-intercept. We would also get our r and our r squared if we had our diagnostics turned on. We don't have to worry about any of that with the testing, okay? We don't have to turn the diagnostics on. We don't need to worry about any of that. We just go over to test. I arrow up because it is at the end of your list of testing. So we have the G is the linear regression t interval, and then F is the linear regression t test. We're going to start with the interval because that's actually what this problem is asking us to do. So I'm going to do G. I've got my X data in list 1, my Y data in list 2. Everything is a frequency of 1. My sea level is actually 0.90 for this example, because it says the problem construct and interpret a 90% confidence interval. Sorry about that, 0.90. My mouse is acting crazy, guys. Sorry, 0.90. Okay, wouldn't matter. And then for the regression equation, what they're asking, kind of like what we did in running our linear regression before, is we would store it in Y1 so that it would graph the line for us, like the line that we see in blue here. If we want it to automatically graph, then what you can do is do alpha trace and select Y1 there. And so then it's going to automatically put that equation that it's going to come up with to fit our data, it's going to put it in Y1 for us, so we don't have to retype it. So let's calculate that, and we should see that we get a lot of this data to match here. So I'm going to blow this back up so we can see it a little bit better. Sorry, I'm moving everything around on you. So we have our B is negative 0.1629. Remember that the B is going to be the slope for us. And so that on this is the miles driven. It's negative 0.1629, so that does match. We have the constant 38,257. Notice that that is our A value on the calculator printout. We have, what else do we have? We have a DF of 14. You don't see the DF of 14 here. Okay, we don't have the DF of 14 here, but let me tell you where that comes from, because you will have to be able to find that yourself. DF, you know, is your degrees of freedom, and they changed it up on us yet again. The degrees of freedom are actually your sample size minus 2 this time. So I pointed out to you when we put our data in the list that we had 16 different data points. So our degrees of freedom is actually 14, because now you're subtracting 2 of the points to get your degrees of freedom. So it's your sample size and then minus 2. Okay, and let's see, what else do we have here? We have the standard deviation of the residuals, the 5,740.13, and then we have the R squared is 66.4. If you move the decimal 2 places to the right, you can see that. And then we have the T and the P if you just scroll down a little bit further. Okay, I've obviously, oh, I'm sorry, I didn't run the test. I just did the confidence interval. Forgive me. We'll see the T and the P in a minute when we actually run the test. I didn't run the test, I just did the confidence interval. So let's check that out from over here and see that they did get the same answers that we got. So they had to work it out by hand because they're doing it just off of the computer printout, assuming that you don't have any of the data. And that's actually how we're going to have to do it on the practice worksheet. We will not have the listed data, okay? And so what we're going to have to do is we're going to have to pick the B, which is our slope. So we're going to start with the negative 0.16292. That's what they started with here, plus or minus our T star. You might want to know, where the heck did this 1.761 come from? So I need you to remember that with a 90% confidence interval, that means 90% of the data is in the middle of the curve. So you have 10% left for the tails to share. So you have 5% on the right and 5% on the left. So we want to do second vars. We're doing an inverse T. So number 4. The area is going to be 0.05, and the degrees of freedom. And our degrees of freedom would be 14. Again, that's because we have 16 points in there, and we subtract 2. And when you run that, we should see the 1.76 as our, so you'll see that we have our t-value of 1.761. Yes, it does come out negative, but that doesn't really matter because you have a plus or minus in front of it. And then the other thing we need is the SE sub B, which is your standard error of your slope. So you come over here to where your slope is, and you look across to where the standard error is, and that's where the 0.03096 came from. Okay, so from there, what they did is they took their they took their 1.761 and they multiplied it by this 0.03096. I got all that right. And that's where this number came from, the 0.05452. And so you want to take your slope, negative 0.16292. You want to subtract the, which actually is the margin of error, the 0.05452. You want to subtract it, and then you can second enter and add it, and you'll have your lower and your upper bound of your interval. Okay, so the lower end of my interval should be negative 0.21744. The upper should be negative 0.1084. Some of you, it might start bothering you a little bit that they're both negative. You're like, why are they negative? We never, we didn't deal with negative intervals very often before. But you have to remember that this line has a negative slope. So it makes sense that the true slope of the true, the real population line, if you will, it probably is going to have a negative slope, because, the pattern that we saw was a scatter plot where, it is leaning negative. So it is okay that the interval is negative numbers, because they're saying that's the interval of where we think the true slope is. Okay, and then you have to write your conclusion. We're 90% confident that the interval from negative 0.2173 to negative 0.1084 captures the slope of the population regression line, and then they're doing it in the context of their problem. The problem was about the miles driven for the F-150 compared to how much it was listed for sale. Okay. One thing that I didn't point out to you that's going to be important for us is when we're doing our write-up, we have to do conditions. Y'all are so used to doing that. We have our 3 main conditions that we always have to do. Our 3 main conditions being random, 10%, and then always, either your large sample or your large counts. Well, here it's a little bit more complicated. They give us this bulleted little mnemonic device or whatever it's called for you to remember, and they call it LINER, L-I-N-E-R, LINER. So the L stands for linear, I stands for independent, N stands for normal, E stands for equal standard deviations, and then R stands for random. So you do still have the random. You might be thinking, wow, 10% is missing. We've always done 10% no matter what. So random's always there. And in actuality, they throw the 10% in with independent for some reason. And so you'll see random still there, and then independent 10% is going to be put together. So if you can remember LINER, those are the conditions that we're going to have to meet. I think they do a really good job of explaining that if I can find the right slide. So here's where they're saying you need to make sure it's linear, you need to make sure your samples are independent, and check 10%. And then normal equal SC, which is kind of confusing. It says the standard deviation of your Y's, you can call it sigma, is the same for all your values of X. So we'll look at the next slide that kind of tells us how to meet that in an easier, less complicated way. And then you have random. The data come from a well-designed random sample, so you'll know that somewhere in the scenario they're going to say that they pulled it randomly. But I thought this did a good job of how you can explain how each of these are met. So you have linear, you want to examine the scatter plot. So, we didn't really look at the scatter plot of our data. So let's say that I'm going to look and see that I'm on slide 11, so I want to be able to go back to that. But on the example I'm looking at, suppose that we just a second. Okay. Suppose that we just had the data and we didn't have the graphs. Okay. So let's say that we just had list 1 and list 2 data, and that's all we had. If you need to come up with these graphs on your own, we did that in chapter 3, but I just want to quickly remind you how to do that. So we have the data in our list. So remember, we can go to second y equals. We can turn the plot on, and then we want to graph L1 and L2. So then you want to zoom 9, and you'll see this scatter plot here. It's drawing in the blue line because when I ran the confidence interval, I told it to store the equation that it came up with in the y equals, the y1. So I went ahead and graphed it, so that's why we're getting this picture here. If you want to get this picture, you go second y equals. You would have had to either run your confidence interval or run your test. Doing either one of those things is going to create a residual list. So you want to graph L1 with your y list as your residual list instead of L2. So to get the residual list right here, I'm going to go to second stat, and I guess I went to the wrong spot already. Let's see, that just went to stat. Let me try again, guys. Sorry, y equals, nope, second y equals, turn it on. So it's not, I'm having issues because my mouse double clicks even though I'm only single clicking, so bear with me. Second, let's hope it doesn't go off. Stat, okay, there it is. Number 7, it would not exist if you didn't run the confidence interval or if you hadn't run a test, okay? So you've got to do one of those things to get the residual to exist. So now it exists, I put it in as my y list, and then I zoom 9 again. And so notice I now have this graph here, okay? So you can kind of see your residual plot. And remember from chapter 3 that you do not want to have a pattern in your residual plot. If you have like a parabola shape, or you have, some type of curve or something like that, then that as a residual plot tells us that the original equation or original scatter plot didn't really fit a line very well. But the fact that this is very scattered tells us that a linear fit was good for the data that we did have, okay? So again, we want to check if it's linear. Examine the scatter plot to check that the overall pattern is roughly linear. Look for curved patterns in the residual plot. If you have a curved pattern, then you want to say no, it doesn't work. Check to see that the residual center at the residual equals 0 line at each x value in the residual plot. So this horizontal line is the line x equals 0. And so they're kind of halfway above it and halfway below it, and that's a good thing. Half of your points are above it and half your points are below it, for the most part, okay? For independent, we want to look at how the data were produced, random sampling, and random assignment help ensure the independence of individual observations. If sampling is done without replacement, then you need to check the 10% condition. Okay, so we want to say independent samples, and then we also, like your X and Y are independent, and then you also want to say that the 10% rule is met. So for the example that we did, you have 16 different trucks, I believe it was, Ford F-150s, and you would say, oh, we assume that there's more than 160 Ford F-150s in population or whatever to make sure the 10% rule is met. For normal, you want to make a stem plot, histogram, or normal probability plot of the residuals and check for clear skewness or other major departures from normality. You'll see on the practice worksheet that we're not even able to do this one because they don't give us the data. But if they give you the data, then you're going to need to graph it and show the normal. Equal SD is the one that I kind of find to be a little bit confusing, so let's take a look at that. You want to look at the scatter of the residuals. Okay, so the one I have on my calculator screen right now, above and below the residual equals 0 line. So here's the line of residual equals 0 in the residual plot. The vertical spread of the residual should be roughly the same from the smallest to the largest x value. So they need to be like spread out, half of them above the line and half of them below the line, and you wouldn't want them all clustered together like all on the bottom and then these are all spread out at the top or something like that. So you kind of want them equally spread out. You don't want a cluster of data all close together, a clump of data, if you will. Okay, so that looks kind of, you know, somewhat spread out. And then random, you're usually going to read that out of your scenario and make sure it was random. So there is so much more in the PowerPoint, and I would encourage you to read through the PowerPoint and see all the details of it. But I'm going to go ahead and look at the practice worksheet, okay? Because there's a lot there that we'll get at least the basics that we need to know from the practice worksheet, doing that together. So I'm going to go ahead and clear my RAM over here so that nothing that I did in that problem will affect what we're doing in the practice worksheet now. I'm not quite sure if we need the calculator, so I'm just going to actually pull it at full screen, and then I'll pull it back down if we need, if we ever need to calculate anything. Okay, so 12.1 practice, you should have this worksheet because I gave it out, oh goodness, like a month ago or something now when y'all picked up all the chapter 11 and 12 stuff together. So you should have this. So is there a link between the amount of cigarette smoking in countries and death rates from coronary heart disease? We're just going to call it CHD, coronary heart disease. Below is computer output from a regression analysis of this relationship for 4 randomly selected countries. Sorry, not 4, but 14. So they took 14 randomly selected countries. So you can already see we're getting some random, our sample size 14 from around the world, along with a residual plot. The explanatory variable, I want you to remember, sorry guys, that explanatory is X, and there's that hint that X is in the word. So the explanatory variable is X, and that is the annual consumption of cigarettes per person. And then your response variable is always Y. It's the annual deaths from the CHD per 100,000 people. So what is the equation of the least square regression line based on these data? Define any variables used. So we want to start with Y hat equals, typically in statistics, we start with the y-intercept, and then we say plus or minus whatever the slope is times x. I know that in algebra, we kind of hammer into you guys that you're going to do the y equals mx plus b, where you're doing the slope and then x and then plus the y-intercept. But they do typically do it backwards in statistics, and it means the same thing, so it kind of doesn't matter. But just make sure that your constant stands alone and that the other number does have that x next to it. Okay, so I've got the 65.44 is my y-intercept. I'm noticing that my slope is positive, so I'm going to say plus 0.02268x. Okay, so that would be the least square regression line equation, and it does say we have to define any variables used. So we need to define what y hat is. We also need to define what x is. So y hat is your response variable, but you need to define it in context, not just say, oh, y hat is response variable and move on. No, we need to say it's the annual deaths from I'm sorry, I lost myself, from CHD per 100,000 people. Okay, and then X is going to be the explanatory variable, which is the annual consumption of cigarettes. Per person. And that does it for number one. So we have picked out, again, the constant, also sometimes called the intercept, just to let you know, is here. And then the cigarettes, that word's going to change from scenario to scenario, but that number that's below your constant is always your slope. And that's the number that you do want to put with your x. Okay, number two, interpret the slope of the regression line. So always think of your slope as being over 1, even though it is a decimal. So automatically think of it over 1, and then we know that slope is change in y over change in x. And that's just going to help us get the numbers in the right spot when we're talking about in context. So we want to say as x goes up by 1, y goes up by 0.02268, but in context. So x is our annual consumption of cigarettes per person. So as the annual consumption of cigarettes per person goes up by 1, the other thing, the response variable to the annual deaths from CHD, annual deaths from CHD, the coronary heart disease, per 100,000 people goes up by 0.02268. Okay, if you accidentally switch the x and y, then it's going to be completely wrong. You have to have the 1 with the explanatory variable and the 0.02268 with the response variable. So be very careful of that when you're writing up your interpretation. Number 3, if we're trying to determine the relationship between these two variables throughout the world, is the slope you provided in part A a statistic or a parameter, and explain. So the slope in part A, when we did dy equals mx plus b, that is a statistic because it comes from a sample of data. It comes from a sample of data. Okay, what sample of data? It's only the 14 countries. There's obviously more than 14 countries in the world. So it's only from a sample of 14 countries. It's not from a population. So remember, statistic comes from a sample, where parameter is talking about a population. So we need to be careful of that. Number 4, based on the information given, discuss whether the conditions have been met to use T procedures to make inferences about the slope of the regression line. If you do not have enough information to determine if a condition is met, then indicate what other information or analysis is required. So we need to do liner here. So L is for linear, I is for independent, And within independent, make sure you also discuss 10%. I know it's kind of weird that it fits there, but just stick with that, and then you won't forget. The N is for normal. The E is for exact standard deviations, I think they call it. Weird. And then the R is for random. So you have, or equal, I'm sorry, not exact standard deviations, but they call it equal standard deviations. So the E is for equal, but it's talking about standard deviations. Okay, so does it look linear? I would say yes. Why would I say yes? Because the residual plot is scattered. There's not a true shape to it, a true curve or anything like that. And so, you know, based on residual plot, we could say residual plot is scattered. So we say check. And then do we have independence? I think pulling the samples from 14 different countries, of course, that is going to be independent. Now you can mess up the data if you were pulled out of a sample in Canada and then you moved down to the US and you were used in that sample as well. Like you could totally mess up the data. But for the most part, we're going to assume that these 14 countries and their samples that we're pulling from each, there's no overlap, there's no probabilities of one affecting the other one. So we're going to say, yeah, we believe we have the independence. Let's see what they specified in the actual answer key. They said observations for one country should be independent of observations for any other country. And then they say the population is finite, but there are more than 10 times 14, which is 140 countries in the world. So independent, you would just say each country is independent. Kind of each country check. And then for 10%, we're going to assume more than 140 countries in the world. More than 140 countries. And that meets the 10%, okay? Normal, we really don't have the data we need to get normal because we really can't even graph it or anything because we don't have like the list of data. So on the answer key, it says, to determine whether values of y for a given x are approximately normally distributed, we need to determine if the residuals are roughly normally distributed using either a histogram or normal probability plot. This information has not been provided. So we're going to give it an x and say we need like the x and y. We need the coordinates. We need the coordinates in order to graph them and see what we have, okay? So can't do that one. For the equal standard deviations, it says the residual plot shows approximately the same spread around residual equals 0 for all values of x. I know some of us are really picky, and so we might start counting and be like, wait a minute, there's like 5 above the line, and there's 8 below the line, and there's like 1 on the line, and oh no, that's uneven, but it's spread out pretty well. Like they're not all clustered above, or all clustered below, or all clustered to the right, or all clustered to the left. So it, you know, it is somewhat spread out. So we'll just say, let's see, it is spread out. We'll just say it is spread out and move on, okay? We can be more specific if you want to read the practice answer sheet, okay? It is on Schoology, if you can get to Schoology, because Schoology's been down a little bit today, but that's okay. Moving on. For random, the data came from a random sample of 14 countries. It does say randomly selected countries, so that one also is met. Randomly selected countries stated. Okay, so that's liner number 5. Assuming all conditions have been met, yay, we like that. Construct and interpret a 90% confidence interval for the slope of the least squares regression of annual CHD deaths on annual cigarette consumption. They actually want us to do the state plan, do conclude. So for the state, we are going to, it says we want to construct a 90% confidence interval for the slope of the least square regression line. I mean, you literally are just plagiarizing what they're saying. For the slope entire regression line of annual CHD deaths on annual cigarette consumption. Okay, and then for the plan, it said assume that the conditions are met. I remember reading that somewhere. Assume all conditions have been met. So you don't have to list those, but you would go in and tell them what you're doing. So we are doing a linear regression, like name the test, you know, and it's actually not a test interval. We're doing a linear regression T interval. Okay. For the do, we actually have to work it out because we can't do it on the calculator since we don't have our list of data. And so we would do B plus or minus T star, which we're going to have to find, times the standard error of the B, which comes from our printout. So the B is the 0.02268. The SE coefficient that's next to the B, that is our SE, lower B. And we need to do the T star ourselves. So you would be thinking, oh, well, you did that example at the beginning of the lesson where you found T star to be whatever. It's not the same because yes, it's still a 90% for this one, but now we only have 14 points because we're doing 14 countries. You also could count the residual plot points, and there's 14 points there. So now our DF is not 14, now our DF is actually 12. So we are going to have to find the T star that goes with that. And so we're going to do the inverse T of 0.05, because the 90% is in the middle, so you have 5% on the left, 5% on the right, but now our DF is 12. And again, that's because you do your sample size minus 2. And so now we have a DF of 1.782, not a DF, I'm sorry, a T star of 1.782. Am I going to remember that? Probably not. Okay, let me display again so it can go back to red. Okay, so we have our B is from the chart, it is 0.02268 plus or minus our T star, which is 1.782 times our SE sub B, which is again the standard error of the slopes, is 0.01926. So we need to calculate both of those, the plus and the minus, and that gives us our confidence interval. I'm going to start with the minus just because that'll give me the lower end first. Okay, that should be the lower end, and then second enter, so I can go change my minus sign to a plus sign. And that's going to be my higher end answer. Okay. And I am going to round that, and I'm just making sure it matches the answers on the answer key, which it does. Let me play that again. And so when you calculate this, you get negative 0.0116 to 0.0570. So then we would conclude we are 90% confident that the interval from negative 0.0116 to 0.0570 captures the actual slope of the population regression line relating annual deaths by CHD per 100,000 people to annual cigarette consumption per person in all countries. I'm about to run out of time, so I'm going to just jump to number 6 and assume you can write that on your own, because again, kind of just plagiarizing. And let me talk about number 6 really quick. If you were to perform a test of the hypotheses, the null being beta is equal to 0, that your slope is 0, versus the slope is not equal to 0 at the alpha as 0.1 level, what would you conclude and justify your answer using your result in question 5? So the value we're looking at is 0. And so we want to go back to our confidence interval and say, does 0 fit in there? And yes, it is in there. Okay, 0 is in there, so we would fail to reject. So if you go back and look at the practice answers from Schoology, it says since the 90% confidence interval contains the null value of 0, we cannot reject the null, which obviously that's the same thing as saying we fail to reject the null at the alpha 0.10 level. So they go on to say we do not have convincing evidence that the slope of the population regression line relating annual cigarette consumption per person to annual deaths from CHD per 100,000 people is different from 0. So again, for number 6, you want to check that null value. Is it in your interval? If it's in your interval, you fail to reject. If it's lower or if it's higher than your interval, then you do reject the null hypothesis. Okay. Guys, make sure you watch the Party Sabetti video. I really do want you to watch it if you haven't watched it already on the linear regression. I think it's like video 27 or something like that, but I'll tell you guys in class which one you should be watching.